In this video, we are going to learn how to solve rational inequalities and graph the solution set. And so the first thing we have to do is we have to figure out how our graph is going to be divided up into intervals. And so any value that makes the actual inequality equal to 0 will give us a partition. So if I take the top and I set it equal to 0, then we know there will be a partition where x is equal to 3. And then also any value that would make the rational inequality undefined. And so we know that fractions are undefined when they have zeros in their denominator. So if we also set the bottom equal to 0, that will also give us a partition on our graph. So we also have -3. So notice the graph is split into 3 different intervals. Now, I'm going to simply use test points. So if I choose something smaller than -3, such as -5, I'm going to plug that into my original equation or inequality. So -5 minus 3, and then on bottom, -5 plus 3. And so in this case, we get a -8 divided by -2. But overall, that ends up being a positive number. And that's what we're interested in, not the value, just the fact that it's positive. So in between my -3 and +3, I'll use a test point. Again, it doesn't matter. I like 0 since it's easy to plug in. So then I evaluate 0 minus 3 divided by 0 plus 3. And that gives me -3 over +3. And bottom line is I get a negative value. And then finally, something bigger than 3, I'll go ahead and just choose a 5. So 5 minus 3 over 5 plus 3, that'll leave me with 2 over 8, and what matters is the fact that it's positive. So when we're looking at this particular inequality, we are interested in where it is greater than 0, which indicates positive numbers. And so we can see that on this interval here and here is where we saw positive numbers. Now, it does not include equal to 0, so what that means is at those endpoints, we're going to see open circles. So this is what our graph is going to look like. And then when we write our solution set in interval notation, we would say that from the left, we start at -infinity, and then we stop at -3, and we do not touch it, so close with parentheses. And then we put a union, and then the other part of our solution set starts at 3 but does not touch it, and then continues to infinity. So that would be our solution set. Okay, same thing in our next example. So once again, let's figure out how to partition our x-axis. So what makes that particular rational inequality equal to 0? We're going to find a value of 2. So x is 2. And then makes our rational expression not exist. If we set the bottom equal to 0, then that value is, again, it partitions our graph into 3 different intervals. Okay, so now we will use test points on our 3 different intervals. So I need something smaller than 1. I'll just use 0 since it's easy to plug in. Plugging into my original rational expression, I get 0 minus 2 divided by 0 minus 1. So a -2 divided by -1 gives us a positive value. In the middle, I'm going to have to plug in something between 1 and 2. So I'm going to go with just the decimal 1.5. So when I plug in 1.5 minus 2, that gives me -0.5. And then on bottom, when I plug in 1.5 minus 1, that's going to give me a positive 0.5. And negative divided by positive ends up being negative overall. And then finally, I need something bigger than 2. So I'll simply plug in a 3. So 3 minus 2 on top would leave me with a 1. And 3 minus 1 on bottom would leave me with the 2, which what matters is the fact that overall it's positive. Now, with this particular inequality, we are interested in where it is less than or equal to 0. So that means we're interested in the negative values, which are between the 1 and 2. And since it specifically says equal, that it could be equal to 0, that means that we are going to include those endpoints. So we include the 1 and 2 as part of our graph. So that would be our graph, and then our solution set written in interval notation. So we see the graph goes from 1 to 2, and since it includes the endpoints, we put those in square brackets to show that they are included.